integrals. And then we'll look at definite integrals with the substitution rule. And I'm going to start with 25. The integral from e to the x, the square root of 1 plus e to the x dx. Okay. Remember, when we use a substitution, we are trying to make something easier. If it's an equation, if it's an integral, if it's anything. So we're trying to find, to create a simpler integral at this point. How would I create a simpler integral? Well, I look at e to the x. E to the x is a friendly function. But then I look at the square root, and I know that the square root of a plus b cannot be simplified in any way. There is nothing I can write here to simplify it. So maybe that is my starting point. I'm going to say let u or t or v, whatever letter you want, be this expression. So I denote it by u. This is a function now. It's a function of x. And as you notice, and we know that, any integral without dx or dv or dt, it does not exist. So if I want to change this integral into something easier, instead of having x in it, but have u in it, I also have to create du. Because the integral, I cannot write here dx anymore. If I change whatever into u, dx has to be changed into du. So I have the function. Now I hope we remember the difference between f prime of x and dy. What's the difference? Well, this is the derivative, but this is the differential. And the differential is f prime of x dx. So then I will have to determine du for this function. What will du equal to? Well, 1 prime is 0, e to the x prime is e to the x, but don't forget the x. So now let's see how we change this integral from x all the way to u. I notice that e to the x and dx can be replaced by what?
E to the x dx.
E to the x dx.
Du.
Exactly. Very good. So these are already accounted for. They're right here. So what is this?
Just u.
But the square root. Exactly. Exactly. Awesome. So this is my starting point, but I change it into u, and look, this is much easier now because I know how to continue, right? It's just going to be u to 1/2 plus 1 over 1/2 plus 1. Do not forget the constant c, because this is an indefinite integral. Yes, I have to perform the operations, and I have u to 3/2 over 3/2 plus a constant c, and I have to go back to the notation. Because the integral was given in x, the answer must be in x. So 2/3, 1 plus e to the x raised to 3/2 plus a constant c. Not difficult at all to differentiate both sides, the beginning and the end. You'll get the same answer. We can always check, as I said, indefinite integrals, not the definite ones. Okay, let's look at 40. Stop me if you have questions, please. The integral from sine x divided by 1 plus cosine squared dx. Okay, so let's analyze this one and see if we can do anything about changing it into something much easier. Is there any way of choosing more than one substitution may work? That is always the best to find the best one, right? But we may not find the best one all the time. We may even sometimes get stuck, but that's okay. going back, we have to start with something. Any suggestions? Do we have any suggestions on this? So the idea is to use any notation you want. Let's say y, let y be. This is what I don't like. The fact that the denominator has two terms. No one can simplify this. If a denominator has two terms, there is nothing I can do to simplify. I cannot separate into two fractions because of the two terms in the denominator. That's what I have. But if I start with this, it's not going to take me anywhere. Here's why. I can find dy, but when I do, I have 2. I have cosine x times negative sine x times dx. And I'm in trouble. Because the 2 I can make up. 2 and 1/2, that's not a problem. Multiply by 2, divide by 2, it's the same, it's 1. Sine, I can. The negative is not a problem. I can multiply and divide by 2, by negative 2. Dx is right there, but I do not have this piece. So this is not the right substitution. Good, so let's go back to the drawing board and try to find something else. So the integral is this. And here is my idea. I'm not going to call it y because we already used y. So let's say u. If I use just cosine, then du is negative sine x dx. Not a problem to multiply twice by negative 1. It's the same thing. But now this definitely works. How come? It's simply because this negative and sine and dx represent du, and the denominator is 1 plus u squared. And this is quite nice. Negative stays outside. The integral from du over 1 plus u squared. This we know. Which function prime is 1 over 1 plus u squared? I need the most general antiderivative of 1 over 1 plus u squared.
And tangent?
Arctangent. Very good. Arctangent u plus a constant c. But since this is an indefinite integral, I have to go back to the notation and plug it in. So I have negative arctangent of cosine x plus a constant c. And this is it. Now let's look at definite integrals. It's slightly different. I'm trying to look for some problem that I didn't do last night. Yeah, 67. I don't remember doing 67 last night. On page 414. The integral from 1 to 2 from x, the square root of x minus 1 dx. This is a definite integral, and I am looking for a substitution that would help me determine it, evaluate it. And I will never be able to check. Whatever number I get, I'm just hoping that I was going to just have it. Hopefully it's the correct answer. There is no way I can check. Here I can. I differentiate both sides at the beginning and the end, and I have to get the same thing. But for definite integrals, the answer will be a number. Okay, so again, what I don't like is the square root of a minus b, because it cannot be simplified. So I'm going to think in terms of, okay, let's say if y is x minus 1, dy equals dx. Nice. So this piece will be the square root of y. This piece will be dy. But what about this? Well, I have a way of presenting that in terms of y. How do I present x in terms of y from here? All I have to do is add 1. So this 1 will be replaced by y plus 1. So the new integral, do not copy the limits of integration though. The new integral becomes y plus 1, the square root of y dy. Now, we are not going back. For the definite integral, we do not go back. Here's what we need to do though. We have to create new limits of integration. These limits of integration are for x. When x is 1, 1 minus 1 is 0, so the lower limit is 0. And when x is 2, 2 minus 1 is 1. I cannot copy the limits of integration from an integral in x. Identical limits, I cannot copy them in an integral with y, or in y. Knowing that y equals x minus 1, I have to determine the limits of integration. And we do not go back, because this is going to be a number. It doesn't matter if the integral is in x or in y. I will distribute. So this is the integral from 0 to 1. X times the square root of y times the square root of y will be y to 1 plus 1/2, which is 3/2, plus y to 1/2. So the power here is 1, the power here is 1/2. 1 plus 1/2 is 3/2, and then y to 1/2. Why I did this? Because it's easier to determine the antiderivative. Okay, so now the antiderivative of this is y to 3/2 plus 1 over 3/2 plus 1 plus y to 1/2 plus 1 over 1/2 plus 1. Luckily, I only have to plug in 1, because when I plug in 0, this will be 0 and this will be 0, and that's nice. So plugging in 1, I just get 1 over 5/2, which is 2 over 5, plus 1 over 3/2, which is 2 over 3. So this is 15, and 3 plus 5 is 8 times 2, 16. So again, when we solve definite integrals using the substitution rule, there is no need to go back. Just change the limits of integration from the limits for x to the limits for y, and you get the same number. You can go back if you'd like to, it's fine, but there is no need. Okay. Let's look at the integral from, let's look at 0 to 4. Yeah. Every time we are trying to determine a definite integral from f of x dx, this is a note, very important note. F of x must be continuous on the interval a comma b. So for example, problem 68 on 414, we have the integral from 0 to 4 from x over the square root of 1 plus 2x dx. So a few things, every time we are asked to define a definite integral, for this particular case, x minus 1 has to be greater than 1, and it is. But here, 1 plus 2x has to be greater than 0, 2x greater than negative 1, x greater than negative 1/2. Is that correct? Yes, it is correct. This is pretty similar to the idea of a limit. When we're asked to find a limit, first we plug it in to see what we're looking at. So we can determine this. Again, I'm going to start with the same, let u be 1 plus 2x, and see what happens. Well, du equals 2 dx. And from here we can continue, but I just want to check something else. What if I denote, the whole thing with a square root? If I do that, just want to check whether this is a better substitution. This one works just fine. But then dy will be 1 over 2 the square root of 1 plus 2x times 2 dx. And then I have to solve this for x. No. This is better. Okay. Although it's very nice because I see that dy is all this. But then I'm having slight difficulties. I have to square both sides and then get x as, which is fine, as y squared minus 1 over 2 at the top, which is the same thing, really. Doesn't matter. Okay. Yeah, I'll let you choose. You would like to continue with this or with that. It doesn't matter. They are the same. We're going to get to the same number no matter what. Okay, so since you didn't say anything, I'm going to continue with this one. Okay, so then we are having the integral from when x is 0, u is 1. When x is 4, 4 times 2 is 8, 8 plus 1 is 9. And the denominator is the square root of u, and du is 2 dx. Oh, I already have it here. So I have to multiply by 2 and divide by 2. So there is a 1/2 in front because of this. 2 times dx will be du, but I have an x in here that is left over, and I have to solve for x. So I have u minus 1 over 2. U minus 1 over 2. Okay, so this is 1/2. I have to split it now into 2. Put a 1/2 in front. I'm going to put 1/4. So then the numerator is u minus 1, and the denominator is the square root of u du. And this is 1/4. The integral from 1 to 9. This is u over the square root of u, which is u to 1/2, and this is minus u to negative 1/2. And I think that was slightly easier, but it doesn't matter now. Okay, so we have u to 1/2 plus 1 over 1/2 plus 1 minus u to 1/2 over 1/2 from 1 to 9. So 1/4 outside. When I plug in 9, have the square root of 9 is 3. 3 to the third is 27 over 3/2 minus the square root of 9 is 3. 3 over 1/2, and minus when I plug in 1, I can already flip 2/3, and then plus I have to subtract plus 2. Okay, finally 1/4. 27 divided by 3 is 9, and times 2 is 18, minus 6, minus 2/3, and plus 2. So 20 minus 16 is 14, minus 2/3. And 1/4, and 42 minus 2. So 40 over 4 is 10/3. So the calculations were long because of these square roots. Because of the square root in the denominator, The numerator was nice, but then I had to split it, and then the fractions, and I had to find the antiderivative with those fractions as powers, and that's why we got to calculating, so this was 42 minus, so this is 40 divided by 4 is 10, so I get 10/3. Now, if you're wondering about the other possibility, because I think now that would have been easier, then since we're working on this, why not? So that was the integral from 0 to 4 from x dx over the square root of 1 plus 2x. I just want to, I'm curious now, y equals the square root of 1 plus 2x, and y squared is 1 plus 2x, and x equals y squared minus 1 over 2. And we have du, I meant dy, dy equals dx over the square root of 1 plus 2x. So therefore, now the limits of integration will change when I plug in 0. Yes, I have 1. 4 times 2, so the upper limit is 3. This x will be y squared minus 1 over 2, and everything else will be dy. So 1/2 outside, integral from 1 to 3, from y squared minus 1 dy. This would have been a much shorter way. 1/2 y to the third over 3 minus y from 1 to 3. Okay, so I have 1/2 in front. 27 divided by 3 is 9, and minus 3, and then minus 1/3, and then plus 1. So 1/2, 9 minus 3 is 6, 6 plus 1 is 7, 7 minus 1/3, 1/2, 21 minus 1 is 20 over 3, and I get back that 10/3, but much shorter. That second substitution. So it was a very good example, because it just shows that we may find two different substitutions, and we might get to this, of course we will get to the same answer, but two different substitutions. One is longer than the other. It doesn't mean that this one is bad and this one is good, but this one is shorter. So we learned something from this, that we can find different substitutions and both work. I wanted to also look at 66 as a perfect example, because it triggers one property that we talked about. Any questions for me? Anyone, please? Okay, so